So if you know that you struggle with modelling questions and you drop marks with those kind of questions in exam papers, this video is a video that you need to save because I'm going to go through a summary of exponential modelling. Now, for the purposes of this video today, we're going to use two variables, temperature theta and time t. Doesn't matter what your variables are, but this is a good one. You see this quite a lot where you're modelling temperature against time. So kind of graph like this. Now, really, there are four types of exponential model that you need to watch out for, and I'm going to sketch a graph of what each of these four types looks like. So you may have something like this where you're just exponentially increasing as time goes on. So as time goes on, temperature is exponentially going up and up and up. Now, alternatively, you could have an exponential model where your temperature is just exponentially decreasing, kind of diverging to negative infinity as time goes on. Now, in contrast to the previous two examples where our temperature was either going to infinity or negative infinity, you could have an exponential model where actually your temperature is converging to a limit like this one here. So we're kind of converging closer and closer to this limit. We never exactly touch the limit, but we have a curve that converges to it. And lastly, you could have an exponential model that looks like this, where your temperature is just cooling and it's cooling to this limit. So a good example of this would be like a cup of tea. So you've got a boiling cup of tea, you leave it on the table and it's just going to cool down to room temperature. So that limit would be room temperature. So those are the four types of exponential curves you can have in these modeling questions. So now the general equation for an exponential model is this here. Now, the key thing with these exponential models is that we have two variables, okay? We've got the y-axis variable, theta, the y-axis variable. We've got the x-axis variable, t. Now, the key important thing with an exponential model is that that x-axis variable must be in the power. It must be in the power of e, right? So if that t was like down here, right, instead of the e, it would not be an exponential model. An exponential model needs the variable in the power. So it needs the independent variable in the power, in this case time. So that a at the front is a constant, it's a real value. K is a constant and c is a constant as well. That c could be 0. You see many questions where there is like no c there, it's just 0. So that's the general equation you need to be aware of and you need to watch out for. So different values of a, k and c will give you different curves. So different values will give you curves looking like one of these four options here. Now, if that a was positive and if that k was positive, we can just kind of ignore the c. We don't really need to worry about the c because the c just literally shifts the graph up and down. So we don't need to care too much about the c. We're interested in the shape of the curve. So if that a was positive and if this k was positive, then the curve would look something like this. I'm going to make a note of this here. So if that a is positive and the k is positive, you're going to have an exponentially diverging curve like that one there. Now, let's say that this a was negative, but the k is still positive, then that would be something like this one here. So when that constant at the front is negative, you're just flipping the curve upside down. So a negative a, so like -2 or -3 here, will just flip this previous one upside down. So if k is still positive, you're going to get this curve if that a at the front is a negative value. So a negative, k positive, decreasing exponentially to -infinity. Now imagine instead that a was actually positive and k was actually negative. Now if k is negative, you're multiplying k with time. Now time is positive. I've just written here that time is bigger than 0, of course, in this model. So as time goes on, this t is getting bigger, but k is negative. So when you times a bigger positive number by a negative number, this power that I'm circling is getting more and more negative as time goes on. So e to the -1, e to the -2, e to the -3, so on and so on and so on as time goes on. So something like this, right? Notice how, as time goes on, we get more negative numbers, bigger negative numbers, or negative numbers that are more negative. So that means the numbers are getting smaller. E to the -1 is 1 over e. E to the -2 is 1 over e squared. The denominators are getting bigger, so the numbers are getting smaller. So what's happening here with this curve, if k is negative, this that I'm circling is getting smaller, but because the a is a positive constant, it means that we have a decaying temperature. So theta is decaying. So if A is positive, K is negative, you're going to have a decaying curve that decays to a limit. So kind of like, again, like I said before, a cup of tea, you would have a kind of model where that A is positive, but the K is a negative value. So of course that leaves us with the last option. This option is where both A and K are negative values. So you kind of have like an increasing curve that's leveling off to this limit. Now, again, I just really want to emphasize the difference between a model like this, where your variable t, time, is in the power, compared with a model like this, where your variable t is in the base. This, where the variable is in the base, this is not an exponential model, okay? Not exponential, because again, we need the variable to be in the power to be an exponential model. This is exponential, this is not an exponential model. This is kind of like a power model. Not really sure the real name for this model. I mean, it could be, I mean, if that was 2 there, for example, this K, it'd be quadratic. If that was 3, it'd be a cubic, right? So just some kind of power model. This here is exponential because your variable is in the power. The variable must be in the power. Now, it doesn't actually really matter if that is E or if that's 2, 3, 4, 5. Obviously, we know that E is about 2.7. It's a real value. So as long as that's some real value there, it doesn't matter. The key thing is that your variable is in the power for an exponential model. So what exam boards like to do is they like to ask you for the interpretation of these constants. So again, we've got 3 constants, A, K, and C. So what is the interpretation of A, for example? Well, the way to think about this, if we just plug in time equals 0, so t equals 0. So if we sub in 0, we get theta is equal to A, E, and then to the power of 0, 0 times anything is 0, so 0 there, plus C. So what we get is you get theta is equal to A, e to the power of 0 is 1, okay, 1 times A, plus C. So what we have discovered here is that the initial temperature when time is 0 is A plus C. So the interpretation of A plus C is the initial temperature. Now, usually with a lot of these questions, you usually don't have a C there. Usually it's just this part of the model there without the C. So usually A is usually the initial temperature. So usually that's 0. So in this case, though, if you do have a plus C, then A plus C is your initial temperature. Now let's think about the interpretation of the value of K. So to think about this, what we can do is actually differentiate this curve with respect to T, and that's going to give us the rate of temperature change, okay? So when you differentiate a variable with respect to T, that gives you the rate of change. So when we differentiate this function, remember how to differentiate exponentials. All we have to do is we just differentiate the power with respect to T. So we get K, and then we bring the K to the front. So we end up with AK and then e to the power of KT. When you differentiate a constant, it just becomes 0. So that is your rate of change. So as we can see, this is K times by this exponential term. So K you can think of as like a rate factor in this instance. It's a factor that determines the rate of change of your temperature or whatever variable you're dealing with. There's no specific name for this. I've just called it, again, rate factor that determines the rate of change. It's really important that K is not the rate of change. It's just a factor that determines the rate of change. So just an important distinction. And finally, what is C, the meaning of this C? Now, C is actually either the upper bound or the lower bound for one of these 4 curves. So for example, with this curve here, C is this limit. With this curve, C is this limit. With this curve, I mean, if you were to draw the curve backwards to these negative time values, you'd have a limit up here, and C would be that limit. And C would be the limit maybe down here for this exponential curve there. Let's think about why that is. Now, think about what happens to e to the power of t as t goes to infinity. I mean, go to your calculator, do e to the power of a massive number, you're going to get a massive number. So e to the power of t is going to go to infinity. Now imagine this situation, e to the power minus t. So as t goes to infinity in this situation, well, this is going to go to 0, because imagine you've got a massive negative number, e to the power of massive negative number is 0. So just to summarize, when t goes to infinity, e to the c goes to infinity, but e to the minus t goes to 0. So remember, if k is bigger than 0, that k there is bigger than 0, it means you have a situation like either this exponentially growing curve or this exponentially decaying curve going to minus infinity. So this c is going to be the limit, and it's going to be this limit here, for example, so this asymptote there, or this asymptote potentially somewhere down there, or it could be somewhere lower. So in other words, c is either the upper bound or the lower bound. And remember, if k is less than 0, you have one of these converging curves as t goes to infinity. So again, c is the limit in both cases. So as a summary of this model, A plus C is the initial temperature, K is a factor that determines the rate of change, and C is either the upper bound or the lower bound depending on the curve. So for example, with these two curves, you can think of C as the room temperature as your drink cools or warms to room temperature.